Good afternoon, and thanks rather. Welcome again to the AMC Masterclass series at MINEX Moscow. Again, we appreciate the opportunity to present our thoughts on some of the pressing issues that our industry faces. And again, we've got several AMC experts in the house. But first, I'd like to check in with our Plan, Do, Check, Act cycle that many of you would have remembered from our presentations last year, to see how today's presentation fits in with our overall planning philosophies. In 2018, we looked at preparation for feasibility studies and the lessons that are learned from auditing resources and reserves. In 2016, we discussed strategic planning, meeting objectives of mine planning, and geotechnical servicing for open pit slope stability. In 2017, AMC continued the narrative by focusing on life of mine and presenting papers on the planning cycle, how it can be used across a variety of timeframes, planning grade control strategy and predicting tonnes and grade, reconciliation of actual data with original data used as a basis for design, and geotechnical data management. This year, we focus on the act and plan parts of the planning cycle and how we use geometallurgy to modify our strategies and assumptions for both the study of the project design and plan the activities of the project on the basis of the data collected during exploration and development activities. But why is it necessary to take change and adapt our plans to the basis of new information? As we can see, the continued focus of expanding production and reducing operating costs, in spite of some recent significant improvements in commodity prices, drives the unstoppable decline in ore body grades, as illustrated by this chart. It just continues to decline. So how do we deal with this? We have no choice in this matter, and the principles apply for all commodities that are in a mature state of development. Some mining operations have been able to counter the reduction in metal prices by increasing scale, but for many, this is either not feasible or too capital intensive. Increasing scale can also drive up energy and water consumption. These are increasingly scarce commodities and expensive, for which mining industry often competes against other stakeholders. Increasing prices and reducing costs are an alternating cycle that provides the incentive for reward for innovation. So when this cycle gets out of balance, prices rise and can lead to effects like substitution. So it's in everybody's best interest to help, continue to improve. Geometallurgy helps miners to increase recovery or throughput without necessarily requiring massive capital investment by exploiting the natural characteristics of the ore. Some aspects of geometallurgy, such as beneficiation, have been with us for a long time. The concept of beneficiation, that is separating very low-grade ore from higher-grade material, has been part of mining ever since the start of using gravity to concentrate gold in sluices and riffles. And it continues to be the foundation for many mines around the world. The latest advances now see widespread adoption of scanning technology, coupled with geometallurgical assessment of the ore body to optimise the recovery of valuable materials and minimise ore treatment costs. We'll talk about ore sorting and some of the other exciting applications of geometallurgy a little later. So what is geometallurgy? There seems to be a convergence in the industry to define it as the integration of geological, geotechnical, mining, metallurgical, environmental and economic data to provide the information required to maximise NPV of an ore body while minimising technical and operational risk. The field of geometallurgy is therefore very broad It includes concepts such as geomet, mine-to-mill, grade engineering, ore characterization, ore pre-concentration, beneficiation, and other processes and technologies. Note that all professional disciplines can contribute to the optimisation of a project. In fact, it's the only way to achieve step changes in technology. Let's look at how a geometallurgical study might operate. Keeney and Walters proposed a model loosely structured in 3 phases: data acquisition and interpretation, geometallurgical investigations, which cycle through, and spatial modelling to apply the learnings in an environment that we can use for planning. Ian will provide an overview of this method and talk about some of the data sources and how the information is handled. Evgeny will talk about incorporation of geometallurgical estimates into short-term and strategic optimisation. These concepts have been around for hundreds of years, though they are now becoming more formalised. There are 2 component parts to geometallurgy. We need to notice the differences in properties that are important to processing. And 2, we need data to predict the future response. This second point is where most important advances are being made right now. Yes, it's big data. You'll hear the concept in the media in various areas, but improvements in detection and processing of data now mean that collecting big data is essential. It's not optional. It is easier than ever to collect enormous amounts of data, and this is now driving trends in the industry. More and more companies are collecting the data, and it can provide a wealth of information. Although there are 2 things to be careful of: the quality of the data. Just as drilling programs produce reams of resource information that need audit, the data that we're collecting now in other areas of study needs to be audited to determine the provenance and the quality, because we're going to make decisions in response to that information, and the quality is essential. And the second point is we need actionable outcomes. Collecting the data does not of itself make improvements to productivity and cost control. We need experienced and knowledgeable professionals to interpret the results and recommend the path forward. Okay, so on to today's topic of geometallurgy. We have 3 parts to today's technical masterclass. They'll be presented by Rob Cheshire, who's the General Manager of AMC Brisbane office. He's a metallurgist with 40 years of experience in operations, management and technical roles. His expertise is in corporate and metallurgical consulting, focusing on operational and performance reviews, improvement, optimisation, and in the first half of Rob's career, he's focused on copper smelting and production. More recently, his particular interest is in improving the management and operation of mining and processing facilities. In these roles, he's been involved in studies and reviews at all levels in copper, gold, platinum, nickel, and other base metals. Rob is going to discuss transforming operations with geometallurgy. We've got Ian Lipton, 35 years of mining experience as a geologist, including resource estimation, grade control, feasibility studies, technical audits and reviews, due diligence studies, independent technical expert reports and valuations. He has a wide variety of commodity experience and has been promoting geometallurgy for project improvement for over 15 years. He's been involved in a variety of geometallurgical estimation, hardness and rock strength measurement, assessing the correlations between downhole and geophysical logs, drill penetration and ore hardness, sulfide flotation studies, and using multi-element geochemistry to characterise beneficiation processes. Ian's the author of a variety of technical papers and has presented at Mine Geology, Geotechnical grade control and geometallurgical courses. Ian's going to present on connecting metallurgy to geology. Evgeny Antonov is a mining engineer with 20 years of experience. Since joining AMC in 2007, Evgeny's worked primarily as a lead mine planning engineer on feasibility studies, responsible for pit optimisation, pit design and mine production scheduling in projects in Australia, Africa, Argentina, Kazakhstan and Russia. Evgeny graduated with a mining engineering degree from East Kazakhstan State Technical University in 1998 and was recently elevated to principal mining engineer with AMC. He has an interest in application of different modifying factors to strategic planning and will present on driving optimisation with geometallurgy. Now I'll pass the stage to Rob. We'll take some questions after each presentation and then have a longer session at the end, depending on the available time. Thank you.
Good afternoon. So, this one, you took it away. No? There we go. Good afternoon. So, transforming operations with geometallurgy. It's an exciting topic for me. AMC has been working for several years to develop our expertise in the area. We've been committed to the integration of the disciplines that AMC offers as part of our consultancy, and we've successfully built a geometallurgical capability on the basis of geology, mine planning and engineering, and metallurgical and processing. So we'll talk a little bit about that today and talk about recent developments, and I've some examples to talk about, several quite recent, some from 2 weeks ago at the IMPC conference that was held here in Moscow. There was a very definite flavour of geometallurgy and application to pre-concentration during that conference. It's in the papers, so I'd encourage anyone who's interested in this subject matter to look up the IMPC proceedings and read the papers from there. So, benefits from geometallurgy. Improving knowledge and mapping of the whole ore body. The geometallurgy encourages mapping of mineral species and textures fully, as early as possible, to fully understand the ore body. As Mark said, there's the availability of a lot of data. The tendency in the past has been to design on the basis of average grades and average properties of ore bodies, some domaining perhaps, but not many. In many cases, a surprising number of mines are designed and engineered on a very, very small amount of data. The possibility is there now to collect thousands of data points, not just a few. And with application to resource modelling to build on and augment the resource model, it's possible to have millions of data points with usable parameters for the design of a mine. The trade-off of more data at an accuracy that's achievable early in a project is compelling to get the design process started early, to understand early and to begin looking at options for mine design far earlier than we have done in the past. There's time to do more detailed work later, but there's also time to look at all options early using the information that geometallurgy can provide. Can look at the knowledge of the distribution of deleterious mineral species, talc, organic carbon, oxides. When you're looking for sulfides, it goes on and on. There is information available that can be modelled, and it can be modelled across the whole ore body. Identify pre-concentration opportunities, which we'll talk a little bit more about here soon. It is changing the design of mines across the world now. The ability to put a step before you get to the concentrator, to limit the tons of material that has to be subjected to comminution and the energy that has to be purchased and used in order to complete the processing of ore. That is changing dramatically now using geometallurgical data and pre-concentration based on the models created. Opportunities for mine-to-mill design and optimization is particularly exciting for us. The models that can be created can be used to look at many, many more options for the design of a mine and to seek optimal designs very, very early in a project cycle. In many cases, the design and the sizing of the concentrator can change. Staged construction is possible. Sizing is dramatically reduced, or for the same size, production can be raised if the ore is available. It's widely used already. Lots of examples. This list can go on and on and on now. As a consulting company, AMC, we see a lot of requests for proposals to look at studies. I keep my own poll now. Every RFP that we receive now says, please address geometallurgy. Across all commodities, across all sizes, very common in porphyry, copper with gold. Lots of uses were discussed at the IMPC conference, and many papers were delivered by excited companies that had had successful applications. Some geometallurgical applications, characterization of hardness to assist design of comminution circuits and increase mill throughput, characterizing sulfide mineral assemblage in the ore body and to assist in the design of flotation, for oxide ores in heap leaches, and characterizing blastability to optimize mill throughput through mine-to-mill type programs. All of these can be assisted early by having access to well-constructed geometallurgical models. Sorting ore from waste to increase head grade and sorting ore into grade bins for blending is a big application. Sorting works. It produces steady feed, enables plant operators to settle the plant down and fine-tune parameters for optimized performance. Sorting ore into grade bins followed by sophisticated blending strategies. It's been done forever, but it's being done really well now by mines that realise the potential for this early and design for blending as part of the mine layout. Excuse me. You can blend feed for other parameters as well as just grade. Blending for hardness is regularly practiced. If you understand what the hardness profile is across the whole mine, then you can design for it. You can alter the planning of the mine to produce ore of a specific hardness, and you can anticipate harder areas and not be surprised by them, and certainly not run into the pitfalls that we've seen in the industry where the wrong plant is built. So what can you do with all this information? In many cases, the engineering design of a mine will go as it went before, but with access to geometallurgical information, there's an opportunity to make better decisions early and to spend far less money early in a project cycle to get the optionality fully explored early before you spend a lot of money on detailed sampling and analysis in metallurgical labs. So now I'd like to spend some time talking about, as a detailed example, just to look at pre-concentration itself. It's pre-concentration, it's sorting of ore before you get to the actual plant, right? It's attracting considerable attention due to the potential conversion of non-viable projects into winners and to the improvement in detection and sorting technology that makes it possible. So we're seeing a surge of application of this in the industry now. The tools are there to do it well. So if the potential is there, people are looking for opportunities now to exploit lower grades through smaller plants by pre-concentration. It significantly raises head grade to the plant, significantly lowers the energy and the money required for comminution, and it reduces the per tonne capital expenditure that's required to get the job done. Is that the one? Yeah, so there's various techniques available. Size screening has been used for many years as a pre-concentration method. Bulk sorting is being used more and more, and I'll say a little bit more about that soon with the examples. Particle sorting technology is on the increase, and there are others available. Gravity is used for pre-concentration. Colour is used. Anything you can measure, you can use to do a pre-sort. There are specialty metrics for specialty applications such as diamonds and others. Companies that are using sorting technology now are very, very busy. So if you talk to the providers of sorting technology, they have backlogs in their testing labs. You have to take a number and stand in line if you want to get the big sorting companies to test your ore. So size sorting, I'll just talk a little bit about the 4 bullets from the last slide. Size sorting, use discrimination at the bulk, scale level. It's been around for a long time, but it works. So nickel operators for years have sorted low-grade, oversized material out of their ore to upgrade prior to the plant. Some iron ore mines screen out fines because the fines are lower grade, right? So these are not new techniques. I'm just pointing out that these really are pre-concentration steps. High clay oxidized gold ores, such as many in Russia, have opportunities to screen coarse material, hanging wall material that will appear in the ore. They screen out oversized because they know the grade is in the fines. It's very simple. This is a coal sizer, coal for years. Break with a sizer, a Bradford breaker, or one such as this one, and they reject anything that won't break, because if it won't break, it's low grade or no grade, and they get rid of it. This is a stylized representation of a bulk ore sorting technique. It relies on the sensor to make a determination of material on the belt, all of the material. So not a particle at a time, but it makes a determination of whether or not this material meets a criteria, and there's a yes-no acceptance of the material as valuable or reject. There are many applications that are appearing now. They're facilitated by the success of this step. The better the detector, the better the information, the quicker you can get the number, so the faster the belt can run, like that, right? So the industry is benefiting from the improvement in technology as far as sensors go. This picture was provided by Metso, so they envisaged 25 million tonnes per annum, no problem, right, with detectors. Not all cases, but the potential is clearly there to go at run-of-mine speeds and to do bulk sorting. Iron ore industry has done it forever. Phosphate industry has done it forever, for many, many years. Copper industry is just beginning, right? So many applications of bulk sorting available. People didn't always call it that, but if you can make the determination quickly enough, then you can do sorting and you can design the plant accordingly. This picture you'll see around this is a Scantech machine, but this is an analyzer, PGNAA detector. There are many analyzers around and many techniques are being looked at now. X-ray fluorescence, XRF, near-infrared is looked at, laser-induced breakdown spectroscopy. Right? So LIBS, dual energy XRT is being looked at, EM, electromagnetics, prompt gamma neutron activation energy, which is what this is, PGNA, pulsed fast thermal neutron activation, which is an allied detector, gamma activation analysis, which there were papers on 2 weeks ago at IMPC on successful applications of gamma activation analysis. And so it's not there yet, but people are talking about direct analysis for gold on belt. So not yet, but if you talk to people that are working on it, it's coming. And so for those of us in the gold business, if you can direct analyze for gold on the belt and get it right, then it changes the shape of processing big tons of low-grade gold ore. Right. So some quick examples. These examples, the ones that are dated, these are ASX press releases, so they're publicly released on projects in Australia, mostly in Australia. I just highlight them to point to the fact that people are looking in these areas now, right? And that in order to justify the money to modify a plant, to build a different kind of plant, you've got to have a lot of information early in order to fully look at the whole ore body, not just a one grab sample, not a bulk sample, not one or two domains. You've got to understand the whole of the ore body. So you might have a few samples that you're finding detailed information about, but you've got to relate that to what does the whole ore body look like? What does the whole resource look like to see whether or not you can justify going to the expense of building a different kind of plant. So this is a Kalangiri project in Western Australia. This is a test rig that belongs to TOMRA. TOMRA's European testing people, very, very well regarded, maybe the most successful sorting company, now part of the Autotech group, I believe. But they're particle sorters and they've got great technology for that. However, this project, the reason I picked up on it was it's at scoping study stage now. It's billed as a bulk sort. Really, it's applying their particle sorting, but across the whole of a belt, and so it's sort of a hybrid between particle and bulk. The company is very happy about the results. You know, they're seeing and talking to the outside world about that they're raising grades like this, right? 200%. So life of mine, they're taking the grade up, you know, by 86%. You know, so they're getting numbers that are telling them that they should pay attention to this stuff. $86% increase in copper grade, as we saw in the table, 22% copper loss, 56% reduction in the plant size to do the same job. Throughput decreased from 15 million tonnes per year to 6.6. So that's huge, right? If they can back it up, but these are the kind of numbers that they're talking to the stock exchange about. So certainly at an early stage in a project, which this is, it's worth doing more work. Because if you can make that stick, then, you know, that changes a whole project. This is an older example. Some of you may know Mogalakwena is a platinum mine, a large open pit platinum mine in Africa. Anglo Platinum, working with CRC ore from Australia, the project to use selective blast design to increase mill head grade. So selective blasting using geometallurgical data to target high yield sections of the ore body with greatest blast energy, resulting in fine fragment sizes in high grade material. Lower grade ore is blasted less intensely. Waste is preferentially distributed into coarse size fractions, followed by coarse particle screening to remove oversize and upgrade the ore body. Now, I believe that's a fantastic application of what we're talking about, right? So take an understanding of the ore body, right? Apply sophisticated blasting techniques to manipulate the size distribution and then screen out a low-grade fraction. So this is some of their results, and I believe they're continuing with that, Mark? Yeah? It's ongoing? It's ongoing. Yeah. So, upgraded the feed by 2 to 2.5 times. So, a fantastic example. So, particle sorting. Measurement and separation of individual particles. It's been done forever for diamonds and high value things. And you can read about some of the stones that have been recovered by TOMRA and others by doing sorting. However, others are applying it now. It requires the feed to be thinly spread in a single layer of particles so that individual particles can be detected and rejected or not based on the parameter that's being measured. It feels like the throughput will be low and it's not directly applicable to higher tonnages, but the tonnages are going up, the machines are getting better, and the detector and the source detector combination is being better applied. So there are exciting developments in the field, and as I say, if you talk to Tomra or the others, Steinet or others who are in the field, they're extremely busy now because people want to know, can you do it for me? Excuse me. So this is an example again from a ASX press release, the Rothsay project in Western Australia. There's a particle sorting trial that was undertaken in 2017 using a combination of XRT and then electromagnetic, so to upgrade. And I don't want to try and read this whole thing, but this I was taken with this statement, which comes from a senior officer of the company. What he's saying is that by use of geometallurgical data, they can identify opportunities to use a higher productivity mining method underground, take the dilution that causes in the ore body, and then sort out the stuff that they picked up that they don't want. Now, if you can do that, that opens all kinds of possibilities. So, if I'm looking at my mining engineering friends, they would love to know that you can do that. So change all the numbers on the productivity of the underground mining operation if you can use bigger machines or more appropriately sized machines and not pay the price of dilution for going fast underground, right? So it's great innovative thinking that's driven by somebody finding out early that the material surrounding the ore body is sortable, right? So if you don't know that that's possible, then you don't look in that place and you miss an opportunity early in the project to look at that possibility. This is the Renison Tin Mine in Tasmania. This is a sorting plant that's nearing completion now. So the press release was in July this year. This is a shiny new screening and sorting plant in Tasmania. There's 2 sorting machines. Tin is a particularly amenable sort medium. They can pick the rocks. The sorting is accurate, and there are many applications now. This is just one that I picked because they had nice pictures. But they're very proud of this project. The plant's nearing completion. So the plan is with the same size concentrator. So their concentrator's still here, 720. They can take this much material, they can throw away this much material and get a higher grade into the plant, and the economics of the project come alive, right? So 15 million extra for the screen and sort plant, and less than a year to pay it back, right? So nice project. There's other examples. Once I started looking, I could find plenty, but not much time to talk about them. These ones I just picked up quickly. Lepidolite Hill in Western Australia. this is lepidolite is a lithium ore, a non-desirable lithium ore at the time, a mineral at the time that was discarded. So lepidolite waste following historical mining for petalite, which was a better mineral at the time. So sorting using XRT, jury's still out, but you know, it's obvious in the lithium world that we're in now, if you can pick up someone else's waste that's already been mined and somewhat processed, you might make some money and your operating costs could be very low. So they're excited about that test work, and it's ongoing now. The Gorno zinc project in Italy, it's been picked up and put down a couple of times, but currently they've done XRT, dual energy XRT particle sorting, 60% waste rejection while recovering 94% of the zinc. So those economics might work, you don't know, but that's encouraging enough to tell somebody that they should do some more work. So that's where I thought I'd leave it. We've got some time for some questions, but so my point would be, I would encourage people to spend some money early in a project to know your ore body well. So if you spend some money early on metallurgical data collection, chances are you'll spend less in the long run because you'll do less expensive detailed work later, and you'll also present the mine designers with much more powerful information to take into a pre-feasibility study where they're looking for optionality. So they're not after the most accurate geometallurgical data in the world, they just want to know what does the whole ore body look like, and the opportunity is to do that much more cost effectively than in the past, and there's a compelling reason to do that. And then the opportunity is to carry into the future, once a project starts, an ongoing project to update those geometallurgical models with actual production information, and to keep using them to refine the control strategies, to refine the design strategy of the mine and the control strategies of the processing plant. So.
Okay, are there any specific questions for Rob? We'll have an opportunity at the end for more general discussion on geometallurgy. So I'll pass over to Ian.
Dobry den. Unfortunately, that's in my speech this afternoon. Maybe more next year. We've heard from Rob Cheshire about some applications of geometallurgy. Now we'll look briefly at how geometallurgical data is collected and how it's processed. Mark presented this definition of geometallurgy earlier, and in my presentation I'm only going to focus on a small part of the definition, which is the connections between the geology and the metallurgy. This is where we combine the expertise of the geologist with that of the metallurgist or the minerals processing engineer. And this is about collaboration, about investigation, and importantly, this is professionals working together with common goals. This is the flowchart of a general framework for geometallurgy study, which Mark presented earlier, and you can see the 3 phases which he mentioned. In the past, emphasis has mainly been on the data acquisition phase, at the top here. And during that phase, in the past, typically there wouldn't be very much in collaboration between the geologist and the metallurgist. The geometallurgical approach places much more emphasis on this central part of the cycle. Here we have cycles of testing, data analysis, which are being used to develop predictive, deeper understanding of the ore body and its processing characteristics, not only at the global scale, but importantly at the local scale. And then this information that's derived from here and the relationships from here are captured in the three-dimensional block model. And then the three-dimensional block model can be used as input for strategic optimization, which Evgeny will talk a little bit more about soon. So our best source of geometallurgical data is usually the drill core. Typically we'll have many thousands of meters of drill core spread across the entire deposit, and core provides us with the greatest amount of detailed geological information. And we have things such as rock type, mineral species, grain size, texture, something called rock quality designation, fracture frequency, rock mass rating, which was mentioned this morning, important geotechnical parameters. And usually we'll have, or certainly from a geometallurgical point of view, we'll be requesting detailed multi-element geochemical data. And of course, the core is ideal for performing many of the metallurgical tests that we need to carry out. Looking at the metallurgical side, there's a large range of laboratory tests that can be used depending on the type of ore and the processing method. I'm going to consider crushing and grinding in my talk as an example, because these processes are common to many process plants. And a typical study might use unconfined compressive strength tests, UCS, drop weight test, bond work tests, and sag mill comminution tests, or SMC tests. However, there are some significant disadvantages with these tests, as you can see in the list on the right-hand side. They require a large mass of sample. They're also quite slow to execute, and as a consequence, they're expensive. And typically they destroy the core, so they make it unsuitable for some other purposes. Because of these disadvantages, laboratory tests of rock strength or hardness are unsuitable for detailed mapping of the characteristics of the ore body. So in geometallurgy, we look for other characteristics which we can easily measure in large numbers and at low cost, and from which the metallurgical variable that we're really interested in can be estimated. A variable or a combination of variables with these properties is said to be a proxy or a substitute for the variable of interest. For example, again going back to crushing and grinding, estimation of throughput is important for improving process plant design and day-to-day operations, but we can't measure throughput directly from drill core samples. So typically, in the past, we've tended to use bond work index or drop weight tests to derive parameters for estimating throughput. But the alternative geometallurgical approach seeks to derive an estimate of throughput from a proxy. And when we're considering grinding characteristics, many variables, and there's a list, oops, beg your pardon, there's a list here, many different variables, either alone or in combination, have the potential to form a useful proxy. And you'll be familiar with many of these. As you can see, as we go from the top of the list to the bottom of the list, the cost of obtaining the measurements increases significantly. So the more we can estimate from the top of the list, the more cost effectively we can evaluate our deposit. Point load tests are often considered as a potential proxy for process plant throughput. The point load test is a simple test that's easy to execute on a mine site, easier than the UCS test. You can see the simple equipment here on the right-hand side. But like the laboratory tests, it's relatively slow, it's destructive, and unfortunately the equipment has a habit of breaking down on hard rocks. Therefore, it's not always suitable to be used as a tool to map strength across the ore body. An alternative, and this is just one alternative, but an alternative to the point load test is this thing called the EquoTip hardness tester. It's a small portable device. There's the measurement device, and this is the computer that it's attached to. That can be used on half core, full core, or even quarter core. And it's used to collect very large quantities of closely spaced data. And one of the big advantages is it does not damage the core, so you can use the core for other purposes, and it's all very economical. Here's an example of some EquoTip data from samples which were also used for traditional bond work testing. So on the horizontal axis, we have hardness as measured by the EquoTip tester. And on the vertical axis, we have bond ball work index as measured by the traditional bond work index test. And as you can see, there's an excellent correlation between the two. Now, I'll talk much more about the EquoTip and this particular case history on Thursday in session 13. So if you're interested, please come along to session 13. Returning to our tray of drill core, the process for handling the core could look something like this. By collecting data for a wide range of geochemical and physical characteristics, we can then search to find proxies for response characteristics such as reagent consumption or metal recovery. Note that the extra cost to obtain some of this additional information can be quite small. As we accumulate this additional geometallurgical and geological information, we move into the geometallurgical phase of the investigation. And the main focus in this phase is on establishing predictive relationships. This can be a complex cyclic task, so numerous iterations to derive the relationship. And often there are many variables which can be, have the potential to be used as proxies. So consequently, statistical analysis of the data becomes very important at this point for identifying and modeling predictive relationships. Most importantly, data analysis must be built on good quality data, so quality assurance and quality control should be an integral part of any geometallurgical data collection program. Univariate statistics can also be surprisingly useful. In this examination where we collected multi-element data, the titanium assays, which are shown plotted here, quite clearly showed the presence of 3 different volcanic units within the deposit, which were only partially recognized by geological description of the core. Simple tools like box plots can be very effective at comparing the qualities of different ore types in this example. This is an example from a porphyry gold deposit, and the box plots clearly show the distribution of the alteration minerals in the different rock types. Univariate and bivariate statistics are not always enough. Sometimes complex predictive relationships lie buried in the data, and they can only be identified by their multivariate relationships. So at this time, things like principal components analysis, factor analysis, and cluster analysis can be useful for identifying regions of the ore body that have distinctive characteristics. And then we can use techniques like multiple regression and linear programming to model the predictive relationships so that we can show which combinations of ore characteristics form a proxy for a processing response. Well, I was going to say we can see here, but as the way the slide has come up, we can't see very clearly. Nevertheless, in the picture on the left is principal components analysis used to initially to understand the different regions of the data set. So this is a plot showing one principal component against the second principal component. In this particular study, what was then done next was to divide the data into regions with distinct characteristics, and then from that to develop, using multiple regression, a prediction of, in this case, the A times B sag milling parameter. So this is a parameter used for the design of sag mills, and it's being estimated from a combination of variables. And then in the picture on the right, we see that the combination of variables has been optimized, and we can now see a much better prediction from this case on the right. The third phase of the geometallurgical method is to model the data in 3 dimensions. And any mining software can be used to do this. At the highest level, spatial modeling can be considered in terms of just 3 steps. Firstly, define the volumes. These are the geological volumes and require expert geological interpretation. Secondly, fill those volumes with shapes, and typically what we use is a block modeling technique, which this isn't exactly what it looks like, but it's the same principle. And the block model provides a 3-dimensional grid of points on which we can attach some estimates of, for example, grade or recovery. And then the third step is to estimate the variables into the block model. The grade and the geometallurgical characteristics of each block can therefore be estimated. Geostatistics, if any of you are familiar with resource estimation, you'll be familiar with geostatistics. It provides many different tools to allow the skilled user to estimate a variety of variables with differing statistical and spatial characteristics. So the result is that we produce a 3-dimensional model of the deposit that predicts not only the grade of the mineral that we're interested in, but also can predict the response of various ore types to processing at the local scale. Many variables can be estimated using the same techniques that are used for grade estimation. However, some geometallurgical variables must be treated differently. Many geometallurgical variables are not what we call additive, and I'll give you some examples of what additive means in a moment. So estimates of average values may not have any practical meaning, and there can be effects of scale. So let's look briefly at these things. I've given you a definition here of additive, but it's easier to explain by looking at the 3 examples that we've listed here. So we'll look quickly at the idea of support, we'll look at the idea of nonlinear variables, and we'll look at the idea of whether an estimate is actually meaningful. The first thing we need to check when we're estimating the geometallurgical variables is whether they all have the same support. Sample support refers to the length or the area or the volume or the mass or even the time period which is associated with an observation or measurement. And the principle is that all the measurements that you're considering in your estimation process must have the same support. So there are 3 examples here in which if we simply take mathematical averages, then we don't actually get the correct result, because in each case the support of these measurements is different. So in all cases they need to be weighted by either the length or the mass, etc. Another question in geometallurgical variables is the relationship linear? And many relationships are not linear in geometallurgy. For example, a process plant throughput is commonly estimated from a hardness parameter such as bond work index. the relationship between throughput and bond work index is not linear. It's not linear in the main portion of the distribution, and equally it's typically capped at both the top end and the lower end. So if we had a single sample, A, with a bond work index of 16, we might expect it to have a throughput equating to about 4,659 tons per hour. That's fine. But if we had two parts of the ore body, one with a bond work index of 13.5 and another with a bond work index of 18.5, if we simply take the average of those, then we produce an incorrect estimate of, the average would be 16, we would produce an incorrect estimate of what the throughput is likely to be. So with soft ore in that mixture, the soft ore is going to go through the plant much quicker. So the real average for those is likely to be more like 5,300. We also come across this same problem with geotechnical data. So there's this parameter called rock quality designation, which is a measure of the proportion of solid pieces of core. It does not make sense to average very fractured core, such as this example on the left, with very solid core. To say that the average of those two is this is not meaningful in any mining sense. So for example, in a mine, material like this will cause the failure of the mine slopes or the underground openings, and this is not halfway between in terms of the way the mine will behave. And in addition, we need to consider the effect of scale on the predictive relationship. So when we're looking at, for example, flotation recovery based on small-scale tests in the laboratory, the results that we get are not directly the same as those we will actually achieve in production, because there are many differences at the operational scale, and some of those differences are listed here, which I'll let you read in your own time through the material that's presented later on. So to summarize, a successful geometallurgical program requires collaboration, inquiry, is an iterative process, and must be carried out with common goals by all those involved. So all of the disciplines, geology, metallurgy, mine planning, etc. The identification of what we call proxy variables is a very important part of geometallurgy. As the data sets become larger and more complex, multivariate data analysis becomes more important. And when we want to estimate those things in 3 dimensions, we have to be aware that many of the geometallurgical parameters are not additive and therefore require special modeling techniques. So now I'll hand over to Yevgeny, who I believe is going to talk about how geometallurgical models can be used for strategic optimization of the whole mining business. Thank you.
Is it the same presentation or the next file? It's here. Добрый день.
Good afternoon. As my colleagues has just said, I will be talking about the use of geometallurgy to optimize mining. At our company's geometallurgy can be used both to improve the day-to-day control in short-term planning or to introduce principal source parameters for the entire strategic planning of the whole company. This data can also be used in optimizing the processing and treatment schedule. It is used in the strategic estimate of different options that are more compatible with the corporate goals. The optimal sequence of mining operations is not always relies on the parameters of certain minerals. The most realistic description of such variables, of such indicators, can be the productivity, power consumption for crushing and milling. Also, we have to take into account the effect of impurities that can have an impact on hardness and also on their content in the concentrate. Also, the environmental issues related to both ore body and tailings. As an alternative, we can apply several options: leaching, stacking of certain types of ore for further processing, but everything depends on the selection of mineralogical and physical properties of the ore. So the geological observations and current information that processed to determine the cost equivalent of each ore block in a block model. So we have to update the schedule as operations go on. It may take 1 year, months, 1 day. And also they're used to make use of the advantages of ore control. And for this, with this aim in view, we need to automate these processes that was mentioned by my colleagues in the previous presentations. As an example, I can cite here the big Batu Kejau pit in Indonesia, which has been in operation since 1999. Batu Kejau, 55 million tons per year, 1 gram per ton of gold. The end product is a sulfide flotation copper and silver concentrate. To improve short-term forecast, we included tests, flotation tests that were done during the sampling after blasting operations. We also looked into the copper content in the ore body so that we could get enough information for crushing and flotation. And we also estimated and did an analysis at the temporary ore stacking or warehousing facilities. You've seen this diagram already, optimization of strategy, geometallurgical model, which is the basis, the backbone for improvement and optimizing the mining operations for increasing productivity, crushing and milling that will allows us to create the best project of a certain mine operation, expecting the maximum profitability of a certain project. Geometallurgical approaches for each ore block include more parameters that have more effect on potential revenues, reflecting the costs in each of the options. At the current mines, such approaches allow us to optimize the post-production activities and to get a more stable outcome even at the processing stage. Optimizing production in comparison with optimizing the elements is quite an important indicator. A mining company comprises several activities and several facilities so as to get the end product. The decisions made may affect the different stages of these operations. When certain decisions are made in isolation from other processes, can hardly be optimal and sometimes may have unpredicted consequences for the entire company operation. As an example, the investors have decided to buy a grinder or a crusher for 20 million tons, which can be bought at a discount, and that's why they decided to change the entire production process. Although, logically, the crusher could could probably spend less on 15 million ton equipment, thus reducing their costs eventually. So they saved in one point, but they lost much more in another instance. So what they need is a more comprehensive approach towards such activities. Well, of course, they should first of all think about a more realistic estimate of certain parameters that may affect their activities. Optimizing production. One can say that on the whole there are two general methods for optimizing business in mining: the change of strategy and the optimizing the strategy. The selection of strategy is the conventional approach. Optimizing strategy is a more flexible method which ensures that you can get a better choice. So let's get to the conventional process of selecting a strategy. So here is the rough diagram how it happens. So we are facing certain production goals, the time schedule for extraction and processing. So there are different models, revenues and losses. There are certain drivers. So apart from that, there are corporate tasks. As a result, you make a decision. So there are several options in such a conventional method, but in the meantime, the sensitivity analysis for each of the options is normally performed after the process is complete, so as to understand the most sensitive points of a certain project. But usually the sensitivity is demonstrated, is related to the, is linked with the sale of the product. However, this approach does not reflect how these indicators can be changed in reaction to some external problems, because the price of the product is an external problem. It is not under our control. So under such an approach, the basic schemes are not, do not change. So we carry out a sensitivity analysis for each of them, and one of the strategies is chosen as the best one. But the key shortcoming of this approach is that we have to change the strategy only out of those that are under review, which does not mean that this is the best strategy. So, but here is a typical process of strategy optimization. In this particular case, instead of comparing several options, we use this so-called value peak, so which is presents a more flexible approach towards business optimization. So instead of limiting ourselves to a certain selection of options, we make a decision within the company how to best to treat this project in general. So, for example, we compare the tailings and the product output. So this flexible model can be built so as to reflect all the potentially important components, either the actual or corporate. The corporate model can also be built into the project. The production limitations are not fixed, so they may change. So depending on the choice of the strategy, we can make a decision as we know what changes take place in certain components and whether they can affect or do not affect the final outcome. So these estimates allow us to build up models, links between different models. The so-called value peak takes into account limitations and possibilities of the entire company. The optimizing strategy allows the owners, makes it possible to choose the strategy that is best, the most compatible with their company activities. The typical value peak is depicted here as a kind of a dome, cut beneath. In this particular case, is one of the examples that we wanted to cite here. The ore body were represented several types of mining mass comprising different minerals, different end products, and various characteristics, also various oxides and characteristics in the dump sites and tailings sites. Well, of course, it also affects the environment, and there are certain social issues that are related to this particular. So there's the equivalent copper content calculated respective the cuprum, aurum, and argentum, gold and silver content. So the content in the ore, the equivalents were split into separate contents, so as to that helped us to estimate the added value more accurately, taking into account different recovery rates in different contents. Also, there was another parameter that we used, the productivity of crushing, depending on the material hardness, as it is one of the bottlenecks in the processing and reprocessing, which also allows us to save and to reduce costs in the grinding and crushing operations. There's another example that I wanted to cite is an open pit mining copper gold ore. Well, in fact, here in the milling, we actually evaluate the typical productivity, not the design capacity of productivity. So the different components such as hardness, using the new method allowed us to evaluate the productivity, taking into account the optimal parameters of in crushing and milling. That allowed us to optimize the process during the subsequent years. To analyze this, after analyzing this, we submitted the results of this to the regulators, taking into account the neutralization of ore body dump sites and tailings, taking into account the costs, and also proceeding from the pyrite content, potential oxidization, and also costs related to neutralization of oxides were reflected in the block model depending on the pyrite content. Therefore, it was included in the optimization process at this, both at the stage of optimization and planning. There's another example, the underground non-ferro deposit. So this, we were looking into ways to raise the economic efficiency using the shrink stoping and other methods. So there is a subvertical trend that you can see here. However, the ore body that were identified with the use of formula of equivalent metal. That in this particular case is formula 2. As you can see, it looks more like a cloud. So that provided vision of mineralization and the configuration. So the ore body that was received as a result of that showed the spaces between the lenses of main ore bodies. So the draw of the roofing pillars was related to the reduction of productivity in that particular case. The relation between the content of equivalent metal and the value of that particular block, that format took into account the difference of factors, the metal price, and the sale price. And so we were able to use the AND algorithm so as to determine the final margin, and that's where we had to use the Formula 1, which reflected the trend with less deviation. So the management of this mine managed to use the relevant links and also to calculate the conditions for the sale and the true value of each block, so as to build a regression formula, so as to establish the linkage between the content and the sale strategy. They used Formula 1 equivalent metal with less dispersion, which thanks to which they managed to get better correlation and the true value of the material. So there's the next example of the underground mine, non-ferro metals. When you look at the mineralization with the position of the new parameter, the vertical zone, especially the next meaning, so we realized there was a need to introduce certain changes in the processing methods, including the vertical or column calculation, and with a priority for spacing. So that allowed us not only to deal with the roofing pillars problem, but also managed to reduce the volume of the actual cement used. So the overall value of the resources was also increased due to a high correlation between the parameters and the content and the true value, which can be applied to the actual meaning of the block model. So this image shows the ratio between the value and the previous descriptor of the content, and we see an increase of about 40% here. But we took into account the preliminary driving and also the draw height. As a result of this analysis, we identified that there was little preparation, and in order to increase productivity up to the required intensification of mining operation, and so as to go over to smaller shrink stoping, allowed us to increase the planning indicators, the figures, because at the time of the audit they were about 85%. In accordance with the decisions that were made, we changed the system of processing the parameters of the board content, and thus allowing us to implement most of the activities, reducing the reserves up to the level which did not provoke any negative reaction from the owners of the project. Such quality decisions were made also under the impact of certain factors which were beyond the technical spheres of knowledge. That's why it was so important to consider all the options so as to make more balanced decisions. So that's about all. If you have any questions, I'm ready to answer. Mark will carry on.
Okay. I just have a few summary comments to make and a couple of brief slides, so please bear with me. Could I just have the presentation back there? So we've seen that the effect of combining metallurgy with geology and then using it in mine planning can give us a much better outcome. One point to note, if you're reporting ore reserves, is that pre-concentration, could I have Yevgeny's, the fourth one back, right at the end? If pre-concentration is used in determining ore reserves, then it's important to recognise that the same conditions exist for determining ore reserves based on the amount of information that you have. So the collection and auditing of data is critical. I'll just switch through. I just wanted to make some brief comments about how this relates to the overall industry. Last year, I discussed anecdotal evidence and tentative trends on how the industry was changing. These are now being confirmed, and we can see that the latest data sees that the industry is on the improve. So this is metal prices improving, this is project pipeline increasing, and this is the value of projects in terms of capital. So we're seeing that the evidence is that the industry is improving in health. We felt it last year, and now it's confirmed. But it's interesting to look at this slump in the period here between 2013 to 2015. We note that it's a period when operating cost cutting was going on. Since then, metal prices have started to improve, and with it, higher valuations for companies. And we can see in consequence that we're seeing more activity in exploration and project development, and the industry is feeling more positive. Returning to the cost code, that peak in price that we saw in 2012-13 also coincided with the higher head grades that we see in this declining curve here. So this period here is where there was cost cutting going on, which led to the ability to process lower grades. But this period in here, where there's increasing values and increasing expenditure, is also seeing a reduction in the overall head grade. So I think it's important to note that as these cycles go on, they all contribute to a reducing cost in the industry, and therefore the ability to process lower grades. Just one quick comment on the overall health of the industry. This is one I put up last year about the discoveries in Russia, and the trends are continuing, except that there is more expenditure now coming in the Russian area. We still see expenditure dominated in the South America and North American areas and in Australia, but this has come up from 2 to 3%. And we find that even though there's only 3% of global expenditure on gold in Russia, they're finding about 10% of the gold discoveries. So I think there is, even though there's been a large increase in the amount of gold found, there's still huge potential for particularly junior and mid-sized companies to operate in the Russian area and for increased discoveries to be made. That's a summary for you to take away afterwards. What we've tried to highlight today is that geometallurgy is a key area of recent advancement. Mine-to-mill type investigations have been touted for many years, but generally the work is often conducted in the plant engineering area and in isolation from mining and resource input. So good resource modelling and mine planning systems are already available to quickly deploy assumptions, as we've seen from Ian's input. So we can quickly assess the impacts on projects and processing parameters, leading to much better planning. So all of us will be available throughout the rest of the conference. Please come to our booth anytime to make discussions. We'll be available after this presentation as well. And we can also make appointments through the conference app, which is very user-friendly, and I'd recommend you looking at it. Throughout the conference, we've got the AMC raffle running again. So we've opened it up today, so any people who won't be visiting the booth on Wednesday or Thursday, you can please drop a card off with Camilla at the back. And we've also got a sheet there as well, and if you'd like to leave your name and address and would like to discuss further details via email, then we're also available for contact as well. Thank you very much for your time and attention this afternoon. It's been a pleasure to be here again, and I'd like to thank the MINEX people for putting on the show, and we look forward to seeing you all throughout the conference. Thanks very much. Questions, of course.
Добрый день, Азарнова.
Людмила Azarnova, researcher VGBU Vins. Can you tell me, please, in your experience, what is the demand for geometallurgy research and your work, and whether they are popular, this sort of papers and consultations, or maybe people just turn to you when something happens in their companies?
In the case in the past is that plants are built and then commissioned, and companies discover that there are issues with processing the ore and the outcomes are not as expected. The increase in determining parameters that are important before construction has become more popular, and it's driven by the idea of collecting additional data at an early stage of production. And as Rob said, we now find that that list of companies are coming to consultants and to testing facilities before they build the plant to understand the ore better and to make a large difference when the plant is constructed. So I think your observation has been correct in the past, and now improved facilities mean that we can do better in the future. And many companies are looking at this right around the world, including in Russia.
И тогда у меня есть второй вопрос. Дело в том, что у нас в
I have another question. We have the method of metallurgical and geological mapping, and this is a fairly old method, and actually this method is very well known and popular to see the content of ore, and the Norilsk Nickel is using this methodology. What is your assessment of the perspectives of geometallurgical surveys in the future? In Russia, of course, in Russia, understanding that we have I mean indigenous technologies which we have here in Russia.
I think there is still very much a place for traditional methods. That's very important. But what we're going to see more and more of is new types of information collected, in particular mineralogical information. So spectral scanning of core to provide more accurate estimates of mineral content are going to become increasingly important. I think over the next 10 years, we're going to see geological logging or geological description completely transformed by scanning technologies.
Я думаю, что я недостаточно корректно сформулировала.
perhaps I will reformulate the questions. We have the indigenous method of geometallurgical mapping exactly on the place of the mine when dozens of hundreds of analyses are being studied. Of course, this is nothing new for us, what you told us. Of course, the resource model is available, and these new methods are available, but it would be also making sense in terms of cooperation of our indigenous approaches and your approaches to the same issue.
That's correct. I think it's important to understand that we are trying to build on the techniques that have been used for many years, both inside Russia and outside. What we're looking for is information at a very early stage in drilling campaigns to make sure that we understand the ore as best we can before construction and operation of the mine occurs. There's a very good part in Ian's paper that he will present on Thursday, which identifies or highlights in one mining operation that the hardness and performance of processing is not related only to the geological structures or the lithology that's identified during the mapping phase. So therefore, if the parameters that are identified in a normal program are applied according to those geological lithologies, then you will get an incorrect answer. And it's only by applying many samples and many tests at a very local scale that you're able to identify the different zones and regions of that particular ore body. Some ore bodies it makes no difference, and just applying to lithology is okay. But in some cases, you can get a much better result by linking the test work to the other parameters.
Спасибо.
Okay, thank you. All right. Unfortunately, we've run out of time. As I said, we're all here for the rest of the conference, and please come and talk to us now, and we can even set up meetings for later on as well. Thank you very much.